I hope we don't have the problem we had Tuesday when I couldn't write. More slides. I probably should boot this other one up just in case. All right, acids and bases. These slides here, we were just doing some of these. This one, here's our answer. So keep that in mind. If you want to check yourself that you're entering the numbers properly, do this problem and see that you get 4.17. I'm not sure what this one is. Let's just get this answer real quickly. You go ahead and do this one. The negative log of 2.5 times 10 to the minus third. .60?
Yeah.
All right, so there's a couple to just test yourself. Okay, yeah, this is coming out of the OpenStax textbook. Yeah, acidic groundwater, eroding limestone away, and you get a sinkhole. It's actually taking away the limestone, and finally then it collapses. Acids, they taste sour. You're familiar with vinegar. You're familiar with eating an orange and just getting that kind of that sour taste. You wouldn't eat HCl. It's a little too acidic. It will eat you. It will actually chew up your tissue. Bases are slippery. If your fingers are slippery from something, I mean, it can be oil, but it can be a base like detergent or a soap that you're working with. You think, well, it's really slippery. You wash and wash and wash, and your fingers are still slippery. You probably have a base on your fingers. Okay, I'm going to talk about two definitions of acids and bases. They overlap a little bit. This was the first one, Arrhenius definition. And just to keep in mind here, an acid, you could actually kind of see the H in the material. So an acid is a species that when dissolved in water dissociates to produce hydrogen ions. Well, HCl has hydrogen, it's an ionic, or it can dissociate to form hydrogen ions. Now we're going to write the hydrogen ion either this way or this way. The hydrogen ion floating around in water, keep in mind there are these non-bonded set of electrons on your oxygen, and if you get an H plus, it's going to associate itself. It's a proton. That's all it is. The hydrogen atom minus its electron is a proton. It's a subatomic particle, basically. It's a proton. And it's positively charged, so it comes in next to here, and you kind of have something like this now. But it has a positive charge on it. Okay, and that is the H3O plus, or hydronium ion, floating around in the water. So that proton doesn't just bounce around in the water all by itself. It actually, consider the water molecule its taxi, and it's being motored around on a water molecule, which turns into a hydronium ion. All right, but where did that come from? Where did that H plus come from? It came from HCl. That's your acid. And a base, Arrhenius defined a base as a compound that when you dissolve it in water, it dissociates to produce the hydroxide ion. That's a base. Well, you can kind of see what is a base. If you see sodium hydroxide, potassium hydroxide, barium hydroxide, magnesium hydroxide, okay, you can actually see that it is a base. It's got a hydroxide in the formula. So that is the simplest definition, and it worked pretty well until we came along with something like ammonia. I'm sorry this font is so small, but we come along with something like ammonia, NH3, and you look at it and you think, that looks like an acid. It's got hydrogens. But actually, when you put this into water, it accepts a proton from the water. It pulls a proton from the water to form the ammonium ion. And what does that do? That generates a hydroxide ion. So you put ammonia in water and it doesn't lower the pH. It's not acidic. It raises the pH. So it is a base. This is a base. And you can't see any hydroxide in there. So that came to the Bronsted-Lowry definition of acids and bases, which you should learn, which is simply right here. Bronsted-Lowry definition. The Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. If the compound is accepting the proton, it's a Bronsted-Lowry base. Okay, so this is accepting a proton from water. So that, in this case, this means water is a Bronsted-Lowry acid. It's the proton donor. All right? And so this is a base. This is its conjugate acid. Let me try to help you understand what we're doing here. This is a base. It's a proton acceptor. Once it accepts the proton, it could now be a proton donor. It's a conjugate acid. So the NH4 plus ion is more likely to be a proton donor at some point in time than it is going to be a proton acceptor. It can't accept another proton. Follow me? So it is the conjugate acid. And here is water. It's an acid. And this is its conjugate base. Associated base. So the water is donating a proton, but it's generating this hydroxide ion, and that is a base. That's what's making this basic. Okay, now I'm going to go back to the first definition of acids and bases just for a second to show you that that the Bronsted-Lowry definition is a broader definition, but it doesn't contradict the Arrhenius definition. It's not like these two are competing with each other. Bronsted-Lowry is just pressing the definition to be a little bit more useful, a little bit more general. So let's just look back here. Here's HCl, and Arrhenius said an acid is a substance that when you put it in water, it dissociates to produce hydrogen ion. But what is it? This is the proton donor. I mean, this is an Arrhenius acid, and it is a Bronsted-Lowry acid. It's an acid by the Bronsted-Lowry definition as well. It is the proton. It's donating a proton to water and forming the hydronium ion. So this is both an Arrhenius acid and a Bronsted-Lowry acid. Do you see that? I don't want you to think because I'm talking about two definitions that they're in two different worlds. This definition, Bronsted-Lowry definition, is just a little broader way of defining things. So we got an acid as a proton donor, a base is a proton acceptor. Here's hydrofluoric HF. HF is all by itself is a gas. But if you bubble it into water, you bubble HF into water, it will donate a proton to the water and form the fluoride ion. And so you have HF is your Bronsted-Lowry acid, H2O is your Bronsted-Lowry base. Yeah, just a minute ago we had this. I want to put them both here for a second just to show you. This is your base and here is your acid. So what I've got here are two equations where you say, well, water here, you're calling water the base. Yeah, it's the proton acceptor. And over here you're calling water the acid. Yeah, it's the proton donor. Okay? So it depends. It depends on what it is interacting with. Ammonia is strong enough to pull a proton over onto it itself and form that ion, to be the proton acceptor. But water,
they just switched it up. They just put a little.
Yeah. So this is the proton donor. This is the proton acceptor. This cannot donate a proton to HF. You're not going to get H2F. All right? Because HF is stronger acid. It's going to be the acid, and water now is the base. Acid-base reactions. Okay, one thing I like all my students to learn is this just general reaction. An acid plus a base forms a salt plus water. A salt. In this particular case, the salt happens to be NaCl, which is table salt. But it can be KCl, potassium chloride. It could be magnesium chloride. Depends on what the acid and the base are. But an acid there's going to be an H, there's going to be an OH, there's your water. And the other two ions are going to go together to form a salt. And so if you have exactly the right balance of acid and base, you end up with salt water at the end. It's not acidic, it's not basic. All right, these slides are just kind of going through some of that again. Proton donor, proton acceptor. So this is the conjugate acid. The NH4 plus is your conjugate acid. NH3 is your base, and NH4 plus the conjugate acid. There's a link between these two things, between the water and the hydroxide. And this is an equilibrium. If you put ammonia in water, you end up with this equilibrium. You have all of those things in the water. You have water in the water. You have ammonia molecules in the water. You have ammonium ions in the water and hydroxide ions. So all of those four things, and it can shift back and forth in an equilibrium, in a balanced way. It can move back and forth. Yeah, and here's the terminology of a base, conjugate acid, acid, conjugate base. Associated. Just think of those two things associated, but they're the opposite. This is your proton donor. This is your, now, can be a proton acceptor. Hydroxide ion is not going to donate another proton, but it could accept one. You add vinegar to this solution. If you add vinegar to this solution, which is an acid, and it's going to donate protons, what's going to accept them? That is. And it's going to shift the equilibrium in this direction. All right, so the concept of weak acids, strong acids, weak bases, strong bases. The basic idea here has to do with the degree of dissociation. Okay, what do I mean by that? And HCl, and one thing to focus in on are these arrows. And usually down here what you would see is something like this. You've seen it on some previous slides. Arrows going in both directions. This is weak. Arrow pointing towards the right. So you're going from reactants to products, and there's just an arrow pointing in one direction. You have 100% dissociation.
So it's strong.
That's strong.
But it's going both ways.
And it's going both ways, it's weak. Less than, or we'll just say partial dissociation. So if you bubble HCl gas, HCl is a gas also, you bubble HCl gas into water, you don't have any HCl molecules left. They all dissociate and they form hydrogen ion and chloride ion. Completely dissociates. So you don't have them bumping into each other and coming back and forming the original molecule, HCl. Same way with sodium hydroxide. You dissolve sodium hydroxide in water, it doesn't just dissolve, it completely dissociates, 100%. So this is a strong acid, this is a strong base. These two, this is a weak acid, this is a weak base. You put acetic acid into water, and about 1% of it dissociates. 99%. 95 to 99% of it stays as this molecule. So what is the effect of that? Why is this a weak acid? Because I put some of this in water and I only get a little bit of this. You follow me? You only get a little bit of the hydronium ion. That is what makes the water acidic. So let's take this a little bit further. Let's just look at the HCl and compare it to the vinegar for a second here. So let's have HCl, and it's 1 molar HCl. Since this goes to 0, it completely dissociates. I put 1 mole of HCl per liter of solution. I'm going to get 1 mole per liter hydrogen ion, and I will get 1 mole per liter of chloride ion. You said you only had 1 molar. How do you get 1 of each? Well, it breaks apart into those two things, right? Every 1 HCl gives you 1 H+. So a mole of it will give you a mole of H+, and if that's in a liter of solution, it's going to be 1 molar hydrogen ion. So now let's take our acetic acid. I guess this could be H3O plus over here, just as well. Notice that it's written that way here. I'm writing it this way here. I like to write it this way. In this particular case, if we were in Chem 1307 studying organic chemistry, I would probably write it that way. But you can see you got 2 different kinds of hydrogens here. This is your acidic hydrogen. These are not. This is in your acetate ion. Here's your acidic hydrogen. So you're going to get H3O plus C2H3O2 minus ions. Now if I put 1 mole per liter of vinegar into water, acetic acid into water, but 99% of it stays over here, I only get 1% of it dissociating. So I would only get 1% or 0.01 times 1 molar or 0.01 molar hydronium ion. I'm not going to get 1 molar hydronium ion because not all of this is breaking apart into ions. Can you follow me on that? Is it too early? All right, that's what makes it weak. This is what makes it weak. Because only 1% of it dissociates, I end up with a solution over here of 0.01 molar hydrogen ion, where on HCl I ended up with something that was 1 molar. 100 times more concentrated. 100 times more acidic. That is why HCl will chew up your skin. You can't put that on your salad. It'll ruin your esophagus going down into your stomach. It's kind of funny, your stomach can handle it. Your stomach can handle that acid. pH of the stomach is like 1.5 or 1, something like that. So your stomach can handle what your esophagus can't handle, or your mouth or your tongue. But your tongue and esophagus and everything can handle vinegar. Why? Because it doesn't dissociate and is a weak acid. We'll see what the pH of vinegar is. It's like 3.5. pH of HCl is 1. And you think, well, that's not a big difference, but remember, we're going to be talking about a logarithmic scale. So the difference between 1 and 3.5 is a huge difference. Huge difference. Lots more hydronium ion. Okay, so that's where we're at. So understand what are acids, what are bases. Understand that there are strong acids and strong bases, and there are weak acids and weak bases, and you should log away in your mind a couple of examples of strong acids and bases, weak acids and bases. All right, we talk about an equilibrium. I just mentioned this. About 99% of it stays as a molecule. About 1% of it will dissociate into that and that. Good. Everything's working this morning. I never even figured out why it didn't work Tuesday. Let's see, where to go next? This is the next slide. Well, let's proceed through in the order things are right now. This is an important number. There are going to be 3 equations in this chapter. This is one of them. I've already mentioned this one and one other one are the 3 main things you need to be able to relate to. This is the water dissociation constant. And it's simply the product of, and these brackets right here, where'd that come from? These brackets right here correspond to molarity. All right, so think molar concentration, molarity. So the Kw is the molarity of the hydronium ion times the molarity of the hydroxide ion. And that is a constant. That product is always a constant, 1 times 10 to the minus 14th. So what that means is if this number goes up, that number goes down, correspondingly goes down, so that the product of the 2 numbers is always 1 times 10 to the minus 14th. If this one goes up, hydroxide ion goes up, hydronium ion concentration is going to go down correspondingly. They're balanced out at this constant, Kw. It's 1 times 10 to the minus 14th. So if you had hydronium ion, well, this is where this really comes from. That was 1 times 10 to the minus 7th molar, hydroxide ion, that is 1 times 10 to the minus 7th molar. So then Kw, the product of this is going to be 1 times 10 to the minus 7th times 1 times 10 to the minus 7th. All right? And when you have 2 numbers, if you have to the same base number exponents, you just add those exponents, right? And you end up with 1 times 10 to the minus 14th. That's where that number is coming from. Because if you had a beaker of water here with nothing in it but water, there's nothing in there but water. There's no acid, there's no base, there's no salt, there's nothing. Water will interact with itself to form a little bit of hydronium ion and a little bit of hydroxide ion. And how much of this will do this? Well, 1 times 10 to the minus 7th moles of water per liter of water will do that. That's not a lot of water. 1 times 10 to the minus 7th moles of water per liter of water will do that, and you'll get 1 times 10 to the minus 7th moles of this and 1 times 10 to the minus 7th moles of that. That's where that Kw is coming from. So even just pure water has a little bit of ions floating around in it from this auto-dissociation, its interaction with itself. And so that's where the Kw comes from. All right, this is going to be an important number. This is going to come up again. All right, so if an acid is added, to that pure water, it raises the hydronium ion concentration, it lowers the hydroxide ion concentration. But in such a way that that product is still going to be that number. So let's say we had 10th molar HCl. And we add that to pure water. And it produces 10th molar hydronium ion. And then I say, well, okay, that happened. What's the hydroxide? What's the hydroxide ion concentration in this water? Okay, Gene, write this down. I see Gene back there with his arms folded. See that? Got to put him to work. That means everybody write this down. So we have this Kw equals this times this, and that equals 1 times 10 to the minus 14th. So now we know, but I want to know, this is what I want to know. This is my unknown. What is the hydroxide ion concentration going to be now? So I want to isolate that, so I have this times this equals 1 times 10 to the minus 14th. Oh, 14th. I want to know the hydroxide. So remember what we've been learning all semester. Isolate the unknown. Right? So our hydroxide ion concentration is going to equal 1 times 10 to the minus 14th divided by what is our hydronium ion concentration? 0.1. What do you get?
0.001.
Well, 1 times 10 to the minus 14th divided by 0.1.
I thought there was 1 times 10 to the negative 13.
Yeah, 1 times 10 to the negative 13. Ashley, this 10 to the negative, 0.1 is actually 10 to the negative 1, right? It's 1/10, 1 over 10, or 10 to the negative 1.
10 to the negative 13.
Okay. So you take that negative 1 up into the numerator, you make it into a positive 1, minus 14 plus 1, 10 to the minus 13th. Okay. I just want to show you how you can kind of use this. When you add HCl to the water now, it's not just pure water anymore. Something has been done to the water to disrupt that hydronium ion concentration, raise it. 0.1 doesn't seem like much, but it's much bigger than 1 times 10 to the minus 7th. That's a huge amount of hydronium ion compared to what's in the neutral water. Okay. All right, so now this gets to the other two equations. Gets to the pH. Now keep in mind with pH, it's focused on the H. Okay? The pH scale is following the hydrogen ion concentration or the hydronium ion concentration. Doesn't matter whether it's acidic or basic. It's always asking the question, how much hydrogen ion is in this solution? If it's acidic, the hydrogen ion is high. If it's basic, it's very low. And so the pH, it's a logarithmic scale. the log of the hydronium ion concentration. It's the negative the log of the hydronium ion concentration, pH. This equation is the reverse of this equation. This is kind of unraveling this equation, or the analog. The analog. Taking the opposite of this is this. If I wanted, so when do you use this equation? You use this equation when you know this. All right? Here's your unknown, pH. You want to calculate pH? You take the negative log of the hydronium ion concentration. If you know pH, but you want to know the hydronium ion concentration, you use this equation. Okay? So that's how really equals what? You can't do this unless you know this. You can't actually do this equation unless you know this number. Well, this number comes off of a pH meter. pH meter gives you pH. So if you got the pH of a solution, you could figure out what the hydronium ion concentration is in that solution. All right, so there's your two equations. And then the only other one is this KW equation. All right, so let's probably deal with this one first. Let me just, let's see, do I have this on a slide? Not yet, so let me put it in right here. So pH. pH is a scale that goes from 1 to 14. And you can see it pivots right here at 7. And you've probably heard, maybe in 6th grade, 8th grade, 9th grade, 12th grade, that neutral solutions have a pH of 7. Okay, well so here's our pH. Here's our hydronium ion concentration. What I just got done telling you is that neutral water, just water with no acid or no base in it, is 1 times 10 to the minus 7th molar hydronium ion. And it's 1 times 10 to the minus 7th molar hydroxide ion. But the pH scale, remember, the pH scale is obsessed with hydrogen, not hydroxide. So here's the hydronium ion concentration in neutral water. Take the negative, the log of 1 times 10 to the minus 7th, and you get
Negative log?
take the negative, the log. So the pH is going to be negative the log of 1 times 10 to the minus 7th. Seven. See, that's where that's coming from. That's where that's coming from. If the hydronium ion concentration was essentially 0, if the hydroxide ion concentration is really high, the hydronium ion concentration would be like 1 times 10 to the minus 14th. And if you took the negative log of that, you get the number 14. So that's why you go from 0 to 14 in pH. A high pH, this corresponds to 1 times 10 to the minus 14th. I just want to always put a 4 there. 1 times 10 to the minus 14th molar, and we're talking hydronium ion concentration. That's really, really low. I mean, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I guess I need to put a 1 there. That would be your hydronium ion concentration. Pretty low. It's almost 0. So at a pH 14, there's almost no hydronium ion concentration. It's all hydroxide ion. Down here, towards 0, 1, 0, you have very high hydronium ion concentration, very low hydroxide. Okay, so let's take our strong, let's take our strong 1 molar HCl. It's going to generate 1 molar hydronium ion. So the negative log of 1 is 0? 0. So something about 1 molar HCl, you got a pH of close to 0 or 0. Tenth molar, I think you would have a pH of 1. Okay, now let's take let's take vinegar, and let's say the vinegar was we got our pH meter, and we found out that the pH of this was 3.57. So we know we got a pH here, right about here, of 3.57. And what do we want to know? We want to know the hydronium ion concentration. Okay, now that's where we got to use this equation. We know our pH. We want to know our hydronium ion concentration. So the hydronium ion concentration is going to equal 10 to the negative whatever the pH was. So it's going to be 10 to the negative 3.57. So that's where you use your 10 to the x key. So 3.57, I'm going to change that to a negative. Second, 10x. On my TI-30, it's not. What'd you say? Hit second and key number 5.
Mm-hmm.
Second 5. Aha! 2.69 7 minus 4. Pretty good, huh?
On the TI-30, how do you put the 3.57 above the?
On the TI-30,
Yeah.
I punch in 3.57.
Uh-huh.
And then I hit the negative plus, I change the sign, and then I just hit second log.
Oh, okay.
Everybody get that? Okay, make sure on your calculator you can get this number from this problem right here. Because on your exam you'll have these kinds of problems, and you need to know how to enter them into your calculator. Don't forget this calculator on the exam day. Yeah, you know, first 2 years of teaching or so, I kind of walked away from these tests. I said, I wonder how many students are getting the wrong answers just because they're not punching their numbers in right into the calculator. They actually know how to do the problem, you know what's going on, but the calculator is confusing them. So you don't want that to be the case. You don't want to understand all of this and have a mechanical problem. Okay. This is just going back to this KW term, the auto-ionization of water. A little bit of water auto-ionizes. You get 1 times 10 to the minus 1 times 10 to the minus 7th molar of this, and 1 times 10 to the minus 7th molar of this. So 1 times 10 to the minus 7th moles of water per liter of water auto-ionizes. Yeah, let's see. Yeah, the pH scale. pH is this. We're always going off of the hydrogen. Maybe I've got this. There is one assignment there where it talks about pH, pOH. So pOH is the negative log of the hydroxide ion concentration. There's no pOH scale. We don't have pOH meters, but pH meters. They're always keying in. So hydrogen ion is the focus. That's what we're focusing on, whether it's high or low. But this one, pH or pOH, pOH comes in handy when you are talking about a base. And you're putting it in water, and you're getting sodium ion. This is a strong base. This is a strong base. So if I had 1 mole of sodium hydroxide and put it in a liter of solution, I'm going to get 1 molar hydroxide ion. And so my pOH is going to be the negative, the log of my hydroxide ion concentration. So the negative, the log of, negative log of 1. Yeah, so the pOH is going to be, equal to 0. So how helpful is that number? Well, this could be helpful, because what you will find is that the pH plus the pOH equals 14. And so if I know the pOH, I can calculate the pH. So the pH is going to equal 14 minus the pOH. So the pH of this solution is going to be 14 minus 0 is 14. Okay, so there is this simple little relationship between pH and pOH, which on some occasions comes in handy. The occasion that it comes in handy is right here when you're dealing with bases, particularly strong bases. And you can easily get to the hydroxide ion concentration, and therefore the log, the negative, the log of that, and then you can figure out your pH. That's the beauty of that. All right, we have a couple. Here's a. I don't know how helpful this would be. This might be confusing. I hope it isn't too confusing. But remember, this is what we're really interested in the most. What is happening with the hydrogen ion concentration in a solution, in the bloodstream, in an acid we've prepared, whatever. And there's a direct, really close relationship there mathematically. The pH is the negative, the log of this. The negative log of that concentration. Yeah, so that's the main thing right there. If you know this, you can calculate that. If you know that, you can calculate this. So if you know pH and you want to go to here, it's 10 to the minus the pH. If you know this and you want to go there, it's the negative log of this. So that's what we're talking about. And this is the main arm of that whole gamish right there that we've been dealing with right here. Going back and forth between hydrogen ion concentration and pH. But then there are these other relationships. Yeah, if you know the POH and you want to know pH, it's 14 minus the POH. All right, so we won't, you can just look at that, but just notice what they're saying. If the hydroxide ion, if you know this, you're starting here. You go to here, this is how you do it. If you know this and you want to go here, this is how you do it. Okay, I need everybody's homework. I think on Tuesday I'll try to bring in a kind of a worksheet on this. We'll do some more problems. We'll talk about titration. Trying to think what else is in here. Titration. We'll do some more problems. I'll hand this back, and be ready for any questions you have on either exam number 3, modules 8, 9, 10, and 11. I'm going to go light on module 10 on that exam, okay? I'm not going to say I'm going to ignore it, but I'm going to go light. It's not going to be much more than these words. I think what I will do on that exam is give you I'll give you a, what do you call that?
Word bank.
A word bank.
Boom.
I don't know what I would do with that, Mark. You have this word bank, all right, and you're going to have some fill in the blanks, and you got to be able to get the right association there. That's probably what I'll do with the module 10 part of this. There might be one calculation on calorimetry. Okay? The calorimetry question. But look closely at 8, 9, and 11 for exam 3, and then that you're also well reviewed for the final on 8, 9, 10, 11. You need to then review 1 through 7. Okay? I'll see you Tuesday. Oh, those of you that came in late, come on up here because I took attendance. We really highlighted those who got here early this morning. Homeworks. What's your homework here? Okay. Ashley. We got Tasneem. What? Viviana. Where are you? Right up here. Viviana? I gotta get the right line. There we go. Okay. Chloe.
Rogers.
I got you. You weren't too late.
Vasquez. Shannon. The last one.
Jean, 1 second, Jean.
Sorry. Michelle.
Did I get you, Michelle? Lucas, I got you. Andreas.
Folders.
Are you down at the bottom here? Oh, there you go. Anyone else? Alejandra. Ali. Ali, you want to be Mark?
Yes, please.
Okay.
Do you have
If it says so, what is the amount of heat? It doesn't say the unit, so you don't have to. Okay? That's good. Yeah, it doesn't say kilocalories or calories, so either way.
I have the same question for this one. Because I'm not sure if I did it right at all.
Q equals the mass times this times, oh, okay, yeah, that should be right. What is this number down here?
The answer for this top part.
Okay.
I just went based off the example we did in class.
Yeah, now look at this. This number, you got 21,161. So if you put that into scientific notation, you're going to just move 1, 2, 3 places. So it's 2.12 times 10 to the third.
Okay, so the second 2 isn't.
Well, you look. I'm looking here at moving that decimal place. You got 21,161. Let's round that off to 21,200. Okay. Now you're moving the decimal point. 1, 2, 3.
Oh, okay.
Oh no! You moved it 4. Okay. Okay, you're right. You moved it 4. That's fine. You got it. I'm sorry. I'm confusing you. You got it. It would be 21.2 kilocalories. Yeah, that's fine. 2.12 times 10 to the
Calories,
fourth. Calories per gram. The units here. The C's cross out, the G's cross out. So the only unit here is calorie.
Oh, okay. Oh, okay.
That's calories. And now you're converting it into kilocalories. So to get from here to here is you converted this into kilocalories. This is calories, and that's kilocalories.
Okay, but is this correct though? Or do I still have to do like one more step?
Yeah, but don't put your answer there. I mean, you should put equals. I mean,
Oh, okay.
It makes me look like you're dividing this number into this number.
Oh, no,
But
no.
you're saying that's your answer.
Yeah, that's the answer.
So put your answer as equals your answer. Yeah, okay?
Okay, so this is just calories?
That's now kilocalories.
Kilocalories.
So you took this, calories, and you're multiplying that by 1 kilocalorie per 1,000 calories. See, that's how you're getting there.
That's how I'm getting the,
Yeah.
okay.
That's why I kind of leave it like that, dividing by 1,000. But, oh, I'm confusing you. All you're doing, I'm sorry, I don't know why. All you are doing is putting that into scientific notation. So it's 2.12 times 10 to the fourth calories. Okay? So forget all of that. That's calories. That is calories.
But the decimal's right?
Yeah, that's right. 2.12 times 10 to the fourth calories.
Okay.
I'm not paying attention to answer properly. Okay? You're welcome.